We are going to start the next topic, that is nothing but the types of stresses and strain. So what are different types of stresses and strain? Okay, we will go through it. But before that we should know what is the generalized definition of a stress and what is generalized definition of a strain. So if we consider the stress, it is denoted by sigma. Okay. The internal resistance which the body offers to meet with the requirement. So we have already gone through this definition. Okay, so whenever we are going to apply a load on the body, it develops internal resistance. Okay, that internal resistance is nothing but the stress. Okay, so another definition is internal resistance per unit area which the body offers to meet with the load. Okay, so internal resistance per unit area is nothing but the stress. So stress is denoted by sigma. Formula is force by area or load per unit area. Okay. The unit of force is Newton and unit of area is meter square. So Newton per meter square, that is nothing but the unit of stress, and Newton per meter square is nothing but the Pascal. Okay. So 1 Newton per meter square is Pascal, denoted by symbol Pa. If you want to convert this into Newton per mm square, then how you will convert 1 Newton? To convert this meter into mm, 1 meter is 1000 mm. So 1000, but as this is area, it is said that it is meter square. Okay, so that's why 1000 square. That is nothing but the 1 into 10 raised to 6. So 1 Newton divided by 1 into 10 raised to 6 mm square. Okay, so this is also mm square. So if you simplify it, it will be 1 into 10 raised to minus 6 Newton per mm square. So if you convert Pascal, that is Newton per meter square, into Newton per mm square, it will be 1 into 10 raised to minus 6 Newton per mm square. 1 into 10 raised to 2 Newton per meter square is nothing but the hectopascal, denoted by symbol HPA. Okay, so if you want to convert this in Newton per mm square, 1 Newton, 1 multiplied by 10 raised to 2 Newton, 1 multiplied by 10 raised to 6 mm square. Okay, so 1 into 10 raised to 2 multiplied by 10 raised to minus 6 Newton per mm square. That will be 1 into 10 raised to minus 4 Newton per mm square. Next is 1 into 10 raised to 3 Newton per meter square. That is nothing but the kilopascal, denoted by symbol K3A. A is capital, P is small. Okay, so if you convert this in Newton per mm square, 1 into 10 raised to 3 Newton and 1 into 10 raised to 6 mm square. Okay, so if we again simplify it, 1 into 10 raised to 3 multiplied by 10 raised to minus 6 Newton divided by mm square, it will be 1 multiplied by 10 raised to minus 3 Newton per mm square. Okay. Then after that, 1 into 10 raised to 6 Newton per mm square denoted by MPA, capital M, small pa, megapascal. Okay. So if we simplify it in Newton per mm square, 1 multiplied by 10 raised to 6 Newton divided by 1 multiplied by 10 raised to 6 mm square. Okay. So again, if we simplify it, 1 into 10 raised to 6 Newton multiplied by 10 raised to minus 6 Newton divided by mm square. Okay, so this 6 and minus 6 get cancelled and it is 1 Newton per mm square. Okay, so 1 Newton per mm square is nothing but the MPa. Last is 1 into 10 raised to 9 Newton per mm square. That is gigapascal denoted by symbol GPa. Capital G, small pa. Okay, so 1 multiplied by 10 raised to 9 Newton divided by 1 multiplied by 10 raised to 6 mm square. Okay, so again if we are going to simplify this, 1 multiplied by 10 raised to 9 multiplied by 10 raised to minus 6 Newton per mm square. That is equal to 10 raised to 3. 1 multiplied by 10 raised to 3 or 10 raised to 3 Newton per mm square. Okay, like this we can simplify this Pascal into Newton per mm square. 1 Newton per mm square is equal to 1 into 10 raised to 6 Newton per meter square. Okay, that is nothing but a megapascal or MPa. Okay, so this is the general term that is we find in university exam. Let us see what are the types of stresses. Okay, so very first type of a stress is direct stress or we can say simple stress. Okay, so this direct stress is divided in two parts. One is a normal stress and another is shear stress. This normal stress is again divided in two parts, that is tensile stress or compressive stress. So what is the definition? Direct stress develops under direct loading, that can be tensile load or compressive load along the axis of the member. Okay, so one of the most important point is that if you consider any element, then the loading or the point of application of the load should be the center of gravity or we can say the axis of that member. So suppose if the load is subjected to tensile load, then that is going to produce tensile stress. If the load is a compressive load, that is going to produce compressive stress. So the direct loading produces internal resistance, that is stress, which can be tensile stress or compressive stress. So let us consider a square element like this. Suppose this is the square element like this. Okay, so this is the square element or we can say square rod is there. Okay, so this is the center of gravity of this element or we can say this is the axis of this member. Okay, so the element is subjected to tensile load P. Whenever it is a tensile load, it is shown like this, that is acting away from the point of application. Okay, so this application of a tensile load will produce internal stress or internal resistance within the body. Okay, so consider this section like this. The load is acting away from the point. Okay, so the internal resistance which is set up within the body is distributed all over the cross sectional area and that also act away from this cross section like this. So this is nothing but the tensile stress distribution over cross sectional element. Okay, so how we can write formula for the sigma T, that is nothing but a tensile stress, okay, that is P upon area, P by area, or we can say force per unit area. This section is a square section, so area will be B square, okay. So this is nothing but the tensile stress, okay. Okay. So tensile stress is considered as positive. Tensile stress is considered as positive. Now let us understand what is the compressive load. Just like this situation will be there. There is a square element like this, as we have drawn it already. Okay, and this is the axis of this element, or we can say this is the center of gravity of this cross section, square cross section, and this is the center of gravity of this cross section having same uniform area, or this we can say this is the prismatic bar with the same dimensions. Okay, so this is the axis of the beam or axis of the element, and it is subjected to compressive stress or compressive force. It is subjected to compressive force like this, P. So as this is compressive load, we have shown like it is acting towards the point. Okay, in this diagram we have shown that the load is acting away from the point. In this diagram we have shown that the load is acting towards the point. So this is the compressive load. Okay, so this will produce a compressive stress within the element along over all over the cross sectional area. Okay, so as this is acting towards the point, the internal resistance will also act towards the cross section. So like this. It is distributed all over the cross section. Okay, so it is denoted by symbol sigma C. It is denoted by P by A. In case of a square element, area will be B square, P by B square. Okay. Generally, the tensile stress is taken as positive and the compressive stress is taken as negative while calculating. Okay, so the next is shear stress. Direct stress is divided in two parts, that is normal stress and shear stress. Normal stress is again divided in compressive stress and tensile stress. Okay, so this is tensile stress and this is compressive stress, and the last type of a direct stress is nothing but the shear stress. Let us see what is shear stress. Shear stress occurs when equal, parallel and opposite forces tend to cause a surface to slide relative to the adjacent surface. We will understand this with the help of the example. So let us consider this is the plate. I am showing big plate, okay, like this, and there is another plate which is stacked over this plate like this eccentrically. Okay, these two plates are connected to each other with the help of a bolt. These two plates are subjected to force P and acting along the axis of these plates. As both of these forces are acting along the axis of this plate, both of them are parallel to each other. Okay, suppose this distance between these two forces is d. Okay, so both of them are parallel, so all of the conditions are satisfied. What? They are equal in a magnitude, the force p and this force p both are equal in a magnitude. They are parallel to each other, separated by distance, constant distance d, and opposite forces. Okay, one is going in a along the negative x-axis, another one is going along the positive x-axis. Okay, so all these conditions are satisfied. So because of this application of these two forces, this bolt is subjected to shear stress along this plane. The stress generated over here is nothing but the shear stress. If the load we are increasing further, okay, if the load is further increased, there are chances that this bolt may fail. Okay, so because of this application of this load, what will happen? The lower portion and the upper portion of this bolt, okay, the lower portion may get slide over this upper portion. Okay, so this bolt may get shift to the another position like this. Okay, so there is a relative movement of this two portion with respect to each other. Okay, so the stress produced along these two surfaces, this surface and this surface, is nothing but the shear stress. Okay, so shear stress is denoted by symbol tau. For stress, we know the definition, that is nothing but the force per unit area. So that is going to remain same, that is P by A. Okay, so P is nothing but the force, and area is nothing but this cross sectional area of this bolt, that is pi by 4 multiplied by d square. Okay, so this is about the direct stress and simple stress. Direct stress is divided in two parts, that is normal stress and shear stress. Normal stress is again divided in two parts, that is compressive stress and tensile stress. Okay, so we have already seen what is compressive stress and tensile stress. Now we have seen what is the shear stress. Now let's move to the next point, that is indirect stress. Okay. Let us see what is indirect stress. Internal resistance, that is nothing but a stress which is not directed along the direction of the acting force, that is indirect stress. So we have gone through the direct stress. What is direct stress? Suppose this is the element, we have already gone through this, but I am again explaining this to you. Okay, so suppose this is the element, and along this axis of this element, the compressive force is acting like this, so having the magnitude P. Okay, so internal resistance is developed along the cross section. Let us consider this section like this. So the direction of the internal stress produced is in the same direction of the applied force. Okay, so that is direct stress, which is directly produced. But when we say indirect stress, you are applying a load in a certain direction, but the stress is produced in another direction. That is, we can give an example. Suppose load is applied in x direction, but applied in a y direction, but stress is produced along the x direction. That is, the stress is produced in an indirect way. That is nothing but the indirect stress. So what are the types of indirect stress? The type of indirect stress are bending stress and torsional stress. These are the stresses which are produced in indirect way. Okay, so let us see what is bending stress. What they have said, when a horizontal structural element is subjected to load which is perpendicular to the axis of the member. So let us consider a horizontal structural element, that is nothing but the beam. Okay, so this is the beam like this, and which is supported on two columns. Okay, and this is the axis of this element. Now the load is acting in a transverse direction, or we can say perpendicular to the axis. Suppose the load is acting like this. These are the various point loads acting along the length of the beam, okay, perpendicular to the length of the beam or perpendicular to the axis of the beam. So this load is not acting in this direction, okay, the load is acting in the direction perpendicular to this axis, okay, like this the load is acting. Okay, so because of this application of this load, what will happen? The beam will bend. So how the beam will bend? The beam will bend like this. Okay, so again this is the axis of the beam. So because of the application of load, the beam has deformed like this, or beam is deflected. Okay, so because of this application of force and because of this deformation, there will be internal resistance will be developed. Okay, so if you see this diagram, the upper portion of this beam is compressed and the lower portion of this beam is elongated. Okay, so that is in a tension and upper part is in a compression. So along this length of the beam, along the axis of the beam, the stress will be generated. That will be nothing but the compressive stress and tensile stress. Okay, so if we draw the stress distribution diagram for this beam, it will be like this. This is the compression and this is tension. Okay, so both of the stresses will be developed. So this is nothing but the flexural stress distribution diagram. Okay, so the load is applied in a transverse direction, but the stress is produced along the axis of the beam. Okay, so this is nothing but the indirect stress. So what they have said, this will cause the member to bend, resulting in a deformation of the material. So the beam is deflected or the beam is deformed. The stresses develop internally, that is tension, compression and shear. Okay, so along this beam there is a compression is also there and tension is there also there, which is along the length of the beam or along the axis of the beam, but load was applied in a transverse direction. So that's why bending stress is nothing but the indirect stress. Okay, so we have covered tension and compression. The last one is the shear. How the shear stress will be produced? So let us consider again a beam like this. Okay, and it is subjected to transverse loading like this. So because of this transverse load, what happens? The beam again gets deformed or again gets deflected like this. Okay, so if we consider in this beam number of layers which are parallel to each other like this is suppose the first layer. Like this we can draw number of layers. Okay, so the beam has deflected like this. The upper portion is in a compression and the bottom portion is in a tension. Okay, so the upper layer of this beam is compressed and lower layers of this beam are in a tension, or we can say they are elongated. So as these layers are in a contact with each other, there will be relative motion of this layer. Okay, so when there is a sliding of this layer, what we have said, that there will be the stress produced, that is nothing but the shear stress. And if we draw the shear stress distribution diagram for this element, for this beam, it will be like this. That is nothing but the tau. Okay, so in the both of the cases what we have seen, the load was applied in a transverse direction, but the stresses were produced along the axis of the beam, along the length of the beam. Okay, in this case there is a bending stress is developed. Bending stress is composed of or consists of compressive stress and tensile stress along the depth of the beam. Okay, and when we say the shear stress is produced along the depth of the beam and it distributed, the distribution is along the depth of the beam and it is throughout the length. Okay, so transverse loading is there, but stress or the shear stress is produced along the length of the beam. So the stress is produced in the indirect way. Okay, so indirect stress has two parts, that is two types, that is bending stress and torsional stress. In the bending stress there is a compressive stress is also there and tension stress is also there. Okay, so we have seen it, and how the shear stress is produced, that is also we have seen. Okay, so how to calculate this, that we will say in our next upcoming lectures. Okay, but this is what about the bending stress. Now we will see what is torsional stress. The next indirect stress is torsional stress. Okay, so torsional stress or torsional shear stress is nothing but the shear stress which is produced in the shaft because of the twisting moment. Okay, and twisting is due to the couple acting on it. So suppose this is the plate which is fixed. Okay, and on this plate we have fixed this shaft like this. Okay, so as it is fixed at this point, I am applying a twisting moment on this shaft in this direction. Okay, so because of this there will be stress developed in this shaft, that is nothing but the torsional stress or shear stress, and this twisting is because of the couple. So if we show the twisting moment on this shaft or couple, suppose this is the D, that is nothing but the diameter of this shaft, and these are the forces acting on it. This is F and again this is F. Okay, so these two forces and as they are separated by distance D, it produces couple and this produces twisting in this shaft. For couple, the force has to be equal in a magnitude. So both the forces have same magnitude. They are opposite in a direction and they are parallel to each other by distance d. So it is applying twisting like this. And as this is fixed to this plate, there will be internal resistance or there will be resisting twisting moment will be developed like this. That is nothing but the T. Okay, so here the twisting moment is is F multiplied by D. Okay, that is distance, that is nothing but the couple. Okay, so this will produce internal resistance or internal stress, that is nothing but the torsional shear stress. Okay, so we have covered all the types of the stresses. The last stress is remaining, that is nothing but the combined stress. Combined stress is nothing but the combination of direct stress and indirect stress. Depending on the complexity of the problem, there will be direct stress will be also developed and indirect stresses will be developed. Okay, so combination of these two will give rise to combined stress. So now we will summarize what are different types of stresses. Direct stress, indirect stress and combined stress. These are basically three types. Again, in a direct stress or simple stress, it is divided in two parts, that is shear stress and normal stress. This normal stress is divided in two parts, that is compressive stress and tensile stress. Compressive stress is denoted by sigma c, and tensile stress is denoted by sigma t. Okay, so how the compressive stress is generated? That is nothing but, consider a element like this, and there is a load, compressive load acting along the axis of this beam, that is nothing but the P. So internal stress develops at any section like this, that is nothing but the sigma c. Just like that, in case of a tensile stress, consider a square element like this, and it is subjected to tensile load along the axis of this member. Then it will be resisted by, the load will be resisted by internal stress like this. Okay, so that is nothing but the sigma t. Okay, so of all these stresses, that is compressive stress or tensile stress, is produced in the direction of the applied load, so that's why they are called as a direct stress. In case of a shear stress, we have taken the example like two plates which are stacked over each other and they are subjected to force like P. Okay, and both the plates are connected by a bolt. Okay, so there may be, because of this application of the load, there may be sliding of this uh, interface or sliding of this surface along this plane. Okay, so the bolt, if the force is excessive, the bolt may break and there will be the relative moment of the bolt along this surface, and the stress produced along this surface is nothing but the shear stress, and it is denoted by symbol tau. Then after that we have gone through the indirect stress. Indirect stress is basically divided in two parts, that is bending stress and torsional stress. So bending stress can be denoted by sigma b or F like this. Torsional stress is denoted by tau, and the bending stress is produced when a beam is subjected to lateral loading like this. This is the beam, and when it is subjected to lateral load like this, and it deforms like this, and it produces compressive stresses and tensile stresses in the cross section of the beam, that is nothing but the flexural stress. In case of a torsional stress, suppose there is a shaft which is subjected to the twisting moment, then torsional shear stress will be developed. Okay, so that is nothing but the example of indirect stress, and combined stress is a combination of this direct stress and indirect stress. Okay, so in this case the stress is not produced in the same direction as the load we have applied. Okay, it is produced in another direction. Suppose you are applying load in x direction, but the load is in the y direction, but the stress is produced along the x direction. Okay, so that is nothing but the indirect stress. So this is all about the types of stresses.